Okay, this is going to be a quick introduction to the concept of how do the areas and the volumes compare to each other when we have similar solids. So first off, just to get you thinking about similar solids, we are talking about go back to the basic definition of similarity or basic concept, same shape, different size, and we would definitely have to have the same solid figure, but we also have to have the same shape. So when I'm looking at row 1, I'm looking at for things that get proportionally bigger or smaller. So we can't just make the height twice as tall between A and B. Height is twice as much, but the radius stayed the same. Therefore, we would say not similar. So if you want to pause the video, you're looking for a similar pair of cylinders and a similar pair of pyramids in row 2. So go ahead and pause it, try to figure it out, and then check. Should have said for row 1, A and D, because you notice that the height is twice as much and the radius is also twice as much. For row 2, the pyramid, you should have said A and C were the correct choice. Had to do a little bit of calculation here, but if you did go ahead and calculate the slant height of my first pyramid comes out to be 15 because we have a base. Half the base is 9, and I have a 9, 12, 15. That's my 3, 4, 5 triangle, or the Pythagorean theorem. And on the other one, we have 6, and we have a height of, if I draw my right triangle in there, we have a height of 8. Again, my 3, 4, 5 triangle. So we do have a common ratio between our heights, 12 to 8, our base edges, 18 to 12, and our lateral edges, 15 to 10. And hopefully you're seeing that that ratio is 3 to 2. Okay? Now, if you want to take a minute and explore, I encourage you to actually calculate for row number 1, A and D, calculate for the cylinders, the lateral area, total surface area, and volume, and compare them. Reduce them as a ratio and figure out what is the pattern there. Do the same thing for row 2, pyramids A and C. I'm going to jump ahead and go ahead and show you the answers. So if you want to pause the video, do the calculations for extra practice. That'd be a great idea. And then you can check and compare with me. Looking at the 2 cylinders, I know I don't have my measurements here anymore, but the scale factor between these two, based on, I know that for certain our radii were 6 and 12, or you could have compared the heights, and we should be getting a ratio of 1 to 2, reduced ratio scale factor. Now, if you go ahead and reduce 48 pi and 192 pi, remember we're thinking of these as a fraction, a ratio, the pi's cancel, and the numbers reduce to 1 to 4. Do the same thing for the next row, and we're getting 1 to 4. And then for the final row, the volumes, we should be getting 1 to 8, just reducing those ratios. You should be noticing something happening here. And I'm going to go ahead and take you through the answers to the next one, and I think we'll be able to come up with some conclusions. Again, scale factor, looking at the actual measurements. So I'm going to start with the base edges. We're 18 and 12 meters. Reduced to 3 to 2, would have done the same thing for any of the corresponding measurements. Next row, the lateral areas, reduced to 9 to 4. Same thing for the surface area, and the last one, 27 to 8 is what we're seeing. Observe. What do you notice? And what I'm noticing is for sure these two are the same. How do I get from the scale factor to the ratio of the areas? And maybe you're even thinking back to last chapter, areas, because when we're doing surface area, we're literally doing 2-dimensional work on a 3-dimensional figure. So we're just calculating areas of the surfaces. And if you remember something about that ratio, we're taking our 3 to 2 when we go from the scale factor to the areas. The ratio of the areas is going to be the scale factor squared. So this is my 3 to 2, and I square both parts. And then when I get to the volumes, 27 to 8, this one's a little bit trickier, but we're actually going back to the scale factor, and instead of squaring it, we are cubing it This would be 3 cubed, 3 times 3 times 3, and 2 cubed, 2 times 2 times 2. And if you think about what we're doing when we're calculating volume, we're calculating 3 dimensions. So if we're changing everything by a factor of something, we're changing all 3 dimensions, and therefore we need to cube it. Go back to here, and you can see that 1 to 2, if I square both parts, 1 squared and 2 squared, 1 squared is still 1, 2 squared is my 4, and then I've got 1 cubed to 2 cubed for my 1 to 8 is where I'm getting that from. Okay, this is a good one to think about, the fact that you're doubling it, but you're doubling it 3 ways when we're talking 3 dimensions. Using that concept, getting to the right page, let's do a quick little bit of summary here. And this is a nice way to think of it. If the ratio of 2 similar solids is A to B, ratio of their areas is A squared to B squared. Volumes is A cubed to B cubed. And I skipped perimeters. We didn't calculate perimeter. But perimeter is, remember, just adding up linear measurements, and therefore is going to be the same as the ratios of the side lengths, or the scale factor. You can do a little bit of practice now thinking which ones would always be cylinders. So if you want to pause the video and do a little bit of thinking, go ahead and do so. Then you can check back. If you're checking back in, you should have gotten yes, always similar for cubes and spheres. The rest of them would have been no, sometimes cylinders, or sometimes similar, but not always. Oops. Last thing we're going to do in this video, and then I'll do another video with some examples, is I just want to fill in this table. So if you want to go ahead and take a look, you can try it on your own, and then you can check back. I'm going to try to go through it rather quickly, but the concept is that anything to do with linear measurements is going to be that A to B ratio, same as the scale factor. So if I have a ratio of 1 to 2, I know we already looked at this idea of 1 to 2, I'm going to take all 3 of the first ones are going to be the same. Ratio of the base areas. Okay, so now I've got areas, lateral areas, total areas. All areas are going to be A squared to B squared. And the final one, volume, can't forget about that. 1 to 8, that's my A cubed to B cubed. So we're definitely going to have some repeats here. Let's look at the numbers. And let's go ahead and make some sense of this. Those are going to be the same. Next row you should be getting 16 to 25. And you might need to grab a calculator for this. We're not squaring 16 to get this number down here. We're taking 4 and cubing it. So you got to go back to the 4 or take the 16 and multiply by another 4 to get 64 to 125. Next one. We're starting with the areas, so starting with the areas and going backwards, we're going to need to take the square root of 16 to the square root of 36, giving me, come on smartboard, giving me 4 to 6, but that can be reduced. 2 to 3 is my reduced ratio. That means that I could have, if I want, and I could have divided by 4 to get 4 to 9, would have been my reduced ratio for my areas. Good for the rest of the linear measurements, 2 to 3. And then my volumes, it's impossible to get from your areas to your volume. You got to go back to this, and now I'm going to cube it. 2 cubed is 8, 3 cubed, 27. So first thing I did in that row was actually go back to here and do the square roots. This time I'm going to go back from my volumes to get my scale factor by doing the cube root of 27 to the cube root of 512. That function is under math on the graphing calculators. It's the third button on the left-hand row of buttons. Third button down, math, it's option 4 to get the cube root. Cube root of 27, you might have already picked up on that one, is 3. Cube root of 512, this is a new one for us, is 8. Squaring, 3 squared is 9, 8 squared is 64, and those would be my area ratios. One final row. Let's do it. Reduce first because I don't have nice square roots. So to go from here to here, I'm going to reduce first and say that this is going to be 245 divided by 5 is 49. That allows me to say that this is a nice square root of 1, which is 1, to square root of 49, which is 7. So I've got the rest of these measurements. I've got the rest of these. Went a little too far with that. Just those first 3 are 1 to 7. 1 to 49. And then for my volume, 1 cubed is still 1. 7 cubed is 49 times 7, which is 343, if I can do my math. That's a good introduction of what's the concept happening here and how do I make sense of the ratios of volumes of similar solids and how does that compare to what we learned about in areas. So if you would like more examples, watch the next video. I'll go through some word problems where you have to make a proportion, use the correct ratio, and solve for either an area, a volume, or a scale factor.